Hello everyone, it's July 25th, Sunday. Alright, let's get into it. What do we have today? Non-negative integers without consecutive ones. Given a positive integer n, return the number of integers in the range 0 to n whose binary representation do not contain consecutive ones. Here are the non-negative integers small equal to 5 with the corresponding binary representations. Okay, among them only integer 3 disobeys the rules, 2 consecutive ones, and the other 5 satisfy, so we have 5. Well, it's a very straightforward requirement. I mean, we go all the way to 10 to the 9th. How many digits is 10 to the 9th? Oh, it's a gigantic number of digits if we want to turn 10 to the 9th to binary. What's that? 10 to the 9th. 10 to the 9th. So we call, I think we call bin. It's not too bad. It's not too bad. So, but if we go on, that's going to be ridiculous. 10 to the 9th, we can't even do on. We can have a little trick, but I don't think the trick will work because you have to calculate 0 to 10 to the 9th, and then that's not going to work. So we need to find patterns, right? Define patterns. So 0 to 5, we can actually, let's try 0 to something, right? So we say, let's say for I in range, let's go all the way to 100, just to give us an idea. Print I and bin I. Actually, bin I we want to only go 2 to the end. All right. So here's what we have. Oh my god. This one, yeah, there we go, you can see all. So 3, right? So we can just write down what we see. So what we see is 3 has a consecutive, 6, 7, 11, 12, 13. Actually, that's not the way to go. Let's just write it down. So consecutive is a 1, 1, right? And then 1, 1, 0, 1, 1, 1. You start to see something? Yeah, it's 1, 0, 1, 1. And 1, 1, 0, 0, 1, 1, 0, 1. Now we're repeating, right? So everything 1, 1 will get, right? Everything 1, 1 will get. Now we go this. Interesting. Okay, so the minimum is 1, 1, right? And then starting from 1, 1, we add 0. 1, 1, right? And then the second tier is 1, 1, 0, 1, 1, 1. The third tier, now we have 4, right? Or we have 4 positions. Now we have 4 positions. We can have 1, 1 at different parts, right? So we can have, say, give 4, we can have 1, 1 at the end. And then in the front can be whatever you want. And then 1, 1 can be in the middle. But then we will have repeats. Right? We'll have repeats. But I guess that's fine if we really have repeats. But anyway, if we look at the last 3, right? So if we say 3, we count as 0, 1, 1, right? 0, 1, 1, 1, 1, 0, and 1, 1, 1. That's, we'll say 3 digits. And when we go 4 digits, we're just gonna go the front we said is 1, and we can go the 3 digits again. Right? So we have the 3 digits. Yep, this one. I think that's all the 4 digits, right? So we have this one, they relate to the 3 digits, and 4 digits has its own. Well, it's actually not this one. So it's just 1, 0, 1, 1, 1, 1, 1, 0, 1, 1, 1, 1, right? So these are the 4 that we carry over from the 3 digits. Now for 4 digits itself, we have with 3 digits, add a 0 at the end, right? We can have, so basically we say at the front add a 0, but that's not going to change anything. So front has add 1, now we got 3. And another one is at the end we can add a 1. Right? We can add the and we can add a 1. And now we have repeats, but repeats, I would like to say repeats shall be fine, but it would be better if we don't have repeats. Anyway, so we let the end add 1, and also we can say the end we add a 0, right? So after we combine all these, so basically we have n digits, and we want to go n plus 1 digit. We got a front add a 1, and a tail add a 1, and a tail add a 0. So now we got n plus 1 digits, but there are repeats in it. Therefore, however many we find, we basically have to do it 3 times. So the idea is, can we make it better? I mean, if we want to add 1 or 0 at the end, it is obvious that anything that starts with 0 is not going to work, right? I mean, that's actually because we start with 1, 1, right? And then we want 3 digits, so we at the front add a 1, and front can add a 0, and at the back we can add a 0, add a 1. But add a 1, that will be repeat, so we have these, actually only 2. And then we add 1 at the front, right? Add a 1 at the back, and add a 0 at the back. But that doesn't catch everything. I don't think we catch everything. We have to. No, it does not catch everything. That's the point. It doesn't catch everything. It has to be everything that have so far. Interesting. It has to be everything that we have so far. That is a lot. That is a lot of numbers. Because it's not just n minus 1, right? To get n plus 1 is not just n digits. It also have to include everybody else. Because we have to add every single one that has occurred in the past. Because if you look at this, all right, 1, 1 appears here. So it's everybody. It's everybody we have, right? If we add a front, we add a 1. These are all unique. That's fine. And we can add at the back, we add a 0. And those will be unique. So the front add a 1, and the back add a 0. Those are all unique. And we can be fine with it, right? We can be fine with it. The problem is, at the back, if we add a 1, that is going to be trouble. Let me do this one more time. So what we have now is 1, 1, 1, 1, 1, 1, 0. Now we want 4, right? And then for 4 digits, we have 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, this one and this one. So again, let's do our trick. So our trick is we first add a 1 at the front, so it's 1, 0, 1, 1, 1, 1, 1, 1, and 1, 1, 1, 0. We add a 0 at the back, so it's 0, 1, 1, 0, 1, 1, 1, 0, and 1, 1, 0, 0. So that's at the back, right? So at the front and at the back. And we need to also add 1. So if you look at these two, compare these two, they're all different. They're all different. So the only trouble we have is when we add a 1 at the end, right? So when we add a 1 at the end, we have 0, 1, 1, 1, 1, 1, 1, 1, 1, 0, 1, right? 1, 1, 0, 1. We actually only have, oh, we have a couple. No, we have a couple that's overlapping. And we need to also combine them together. Whew. I mean, the digit number is So we have repeats. We have this one repeats, this one, and this one repeats. So in total, and then these two are only 3 digits, so they don't count. Right, they don't count. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Let's try 5 digits. So 5 will be this bunch. So we have 1, 0, 1, 1, 1, 0, 0, 1, 1. Right, I have this and this 1, 0, 1, 1, 0, 1, 0, 1, 1, 1. These are predictable. 1, 1, 0, 0, 0. Yeah, it's a 1, 1 at the front. 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, and everybody else 1, 1, 1, 1, 0, 1, 1, 1, 1, 1. Right? If you look at this pattern, we can see that so far we have, right? We have 1 and 2 with 3 digits, 5 with 4 digits, right? 2 with 3 digits, 1 with 2 digits, and add them together, right? Add them together, 2 plus 3 plus 4, that's 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 9. That's guaranteed. We just need to shift either 2 or shift 1 and put a 1. So we counted for this. So everything that's 1, 0 something, we counted for. And everything is everything that's good. This one is good. 1, 0, 1, 1. 1, 1, 1, 0, 0, right? 1, 1, 0, 1. 1, 1, 1, 0, and that's 1, 2, 3, 4, 5. That's 5, right? So it looks like we cover from the front and we cover at the end. Which does that make sense? We cover at the front and then we cover at the end. Yeah, it does make sense. If we have 4, right, then the first one must be 1. Yeah, so these are the large ones. So the first one has to be 1, and then we can have anything in between. Hold on. So what you're saying is we need consecutive ones, right? So given 3 digit, so the first one is 1, right? We want a consecutive 1. We can have, first must be 1, and we say, now we have 2 left, right? I have 2 left. And what we can have is the second must be 1. And then the last one we don't care. So that gives us 2, right? And that's it. That's the only possibility. Now with 4, we say first must be 1, right? And now we have 3 options to choose. Now we can have, if the second is 1, then The last two doesn't matter, so these will give us 4. 2 times 2, 4 different varieties. Or, first must be 1, the second we say we're going to be 0, right? Second we don't know, we're going to be 0. Then, the last two must all be 1, right? So second is 0, and then the problem is transferred into given 2 digits, what is the total number? That gives us 1. So 4 digits is 5, right? Now we go 5 digits. So 1, 2, 3, 4, 5. 5 digits. First must be 1, right? So we can do the second at 1. Then the remaining 3 we don't care. So it's 2 times 2 times 2. That gives us 8, right? Second scenario, first is 1, second is 0. Then the problem transferred into given 3 digits. How many consecutive are there? Which we solved it already. That is 2. Therefore, that's that. For the third concept is 1, 0, 0. Given 1, 0, 0, then we have 2 left, right? And that gives us 1. So 5 digits is 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think I got it. Let me reorganize the thought. So it's going to be dynamic programming, right? So we compute from the front, from the start, and we say for any given digits, any given binary number digits, right? We know the first digit must be 1, and then there are different scenarios. We can say 1. Oh, I know it's the 1, and then we just want to know, that's the total number that we start with a 1. Can we say it's 4 digits? That is 4 digits, right? But 4 digits give us no, it has to be 1. It has to be 1 1, and then the remaining is whatever, right? And then if it's 1 0, then we restart. If it's 1 0, we restart. Okay, so now we have to face. So we have one hurdle is done, right? One hurdle is done. That is, we know from 0 to.
Our goal today is to share information about the end of internship process. Today we will cover the end of internship timeline, the intern evaluation process, what steps you should take before you leave Amazon, and what to expect after you leave. We will provide information throughout the presentation, and we'll include all resources mentioned in the presentation through email as well. Let's get started. During the final 3 weeks of your internship, you will begin wrapping up your project and intern work. Your hiring manager, along with your mentor.
So we have solved one problem. The problem is from 0 to 2 to the n minus 1. Right? We've done that. 2 to the n minus 1. Now the problem is to find the actual number, because we have this n is here. That is an interesting question. So we will have to figure out how do we. So we know. Most interns will have a formal internal evaluation, which will be discussed in detail later in the training. For most interns, student programs will send exit communication along with information. We didn't know where. Oh, that is not a trivial thing. I mean, we're going to turn the value into a binary value, right? So kind of gauge where it is. Right? So like in this situation, there's only 1, right? It's like 1, 1, 0 is not included. So we know 5 is 1, 0, 1. Right? 5 is 1, 0, 1. Wow, this is Alright, so we can compute, right? So whatever number they give us, right, that have a certain number of digits. We can compute the smaller digits until the smaller digits, and that one we can compute, easily compute. So now the problem is from basically say 1 0 0 0 0, whatever, right? That's the first number into that digits until the ones that is our target. How many that we have. Then we have to just go slowly, right? Go slowly. So in that case, we'll definitely first say it's gonna be 0, 0, 0. Like gonna, oh no, it's a 0, 0. It's a two digits, and hmm, hmm. Hold on. Can we Can we do? Probably not. I mean, we can say the value and then minus this, right? Then we turn that into a smaller problem. We turn that into a smaller. It's not really a smaller problem, but we turn it into how many there are between this and this, a smaller value, and then we do this again, right? We do this again.
Complete your intern self-review. Interns are not included in evaluation meetings, but writing a strong self-evaluation ensures your voice is included in the final evaluation. The self-review should be data-driven and include how you progress towards your
Hold on. So what we're gonna do? So given any number of digits, so we're gonna start from two digits, 3 digits, 4 digits, right? So we can do that 2, 3, 4, all the way to a certain value, and then we can have a table, the number of digits, right? So like 2 digits, we're gonna say 2 digits include everything. That's gonna be 1. 3 digits is gonna be 2. 4 digits is gonna be 5. Right? 5 digits is gonna be 11. So we have that, and once we compute to that, and then we just when it shave off the front, right? When it shave off the front, it's called a right shift. When a right shift, is it a right shift or left shift? It's not. It's just a. It's gonna be. How do we get the most significant bit? Most significant bit. We cannot go left, we cannot go right shift. It's gonna be. I got calculate a log. What is the faster way? Well, the faster way is actually do a binary and count how many there are, and then we can exclusive OR like that. Basically, just minus that, so we have the remaining, right? And then we do that value itself. We do that. It's the same thing, and we do that, and we already calculated something, right? We already calculated the previous, so we just use that and then compute from. Basically, we're saying from 1 all the way to whatever that, how many there are. Oh, from 0 to that. This is the same problem. And then once we're done, we just add on top. Let's give it a shot. I think I have an idea. So it's gonna be how can I call it? It's gonna be a DP with recursion. The DP with recursion. Okay. So DP. I think I can get. It's going to be 0 times. It's going to just binary n, right? Binary n, whatever we call binary, it gives you a weird value. We'll give you this. So in the length of this, minus 2, right? That's the so binary this. So in the length, binary this minus 2. That's the largest that I can get, right? So that's the DP table. And what we're gonna do is called def def DP. So no. What I actually call find integers. Right, when I actually call find
Or like
integers.
more information about any portion of the training,
Find
please check
integers
out our
helper.
website. And if
So
you
just
need
call
additional support,
def
you can
helper,
contact the
right?
program team
Helper.
at instant.program@info.com.
Helper, which is gonna
Through the program,
have, we're
we'll issue
passing a
the
num
for your internship.
int and return an int, right? And what we're gonna do is we're passing a number, and we're gonna go from basically from 0 to that. How many do we have? So how do we solve this? We're gonna say we're gonna get the number, right? Shave off the front, call it, and then do the accumulation, right? So what we're gonna do is shave off the front. How do we shave off the front? We call bin num, right? -2 and 1 left shift that many times. Actually, we can try. So that's no, that's not what we want. So we're gonna try. Let's just say a equals 10 to the 9th. That's fine. So we say binary a -2, 1 left shift that much, and exclusive or a. And we're gonna call bin this. Just kind of see if this will make any sense. This does not make sense because I should call len. I forgot to call len. And let's go bin a. So binary a. Oh, I think I shift left too many times. Yep. So it's gonna be actually -3. There we go. If it's -3, call bin a, we remove the top. So that's what we want. So we want it's -3. So we're gonna left shift that much times exclusive or num, and we're gonna say remains equals helper. Right, we're gonna call this. I think it's fine. It's actually len bin num -3, which is for all num. So the remains is this, and of course, if we get down to a number is so we take it away, take away, and eventually, what if it's a 0 something? Oh, if it's a 0 something, that's fine. We just always take away, and eventually, if it's going to be a 0 or 1, right? So we should say if num is 0 or num equals 1, right? So that's the end case. That's going to return 0 because we don't have any. Right? We don't have any. Now we got the remains. Now we're going to compute, right? Now we're going to compute. So actually, we're going to say binary length. So we say bin length equals len bin num, right? And this one we can simplify to bin length. Now we have this bin length, and we are going to secure the first one, right? Secure the first one, and we say, actually no, that's the number, right? And what we want to know is the thing's smaller. Yeah, the thing's smaller, which means it's the, if my number is 5 digits in binary, right? What I want to find is the 4 digit. So the bin length is this. The remains is whatever this, right? But the 4 digits one, so we're going to compute. And we say if dp bin length -1, right? So that bin length is the total length, and -1 is the remaining, the 4 digits length, right? If the 4 digits length is not equal to 0, then we just return dp being length minus 1 plus remains. All right. Otherwise, then we have to compute. How do we compute? We compute by taking that, right? That means this one we haven't done before. So we're going to say dp being length minus 1 is equal to, and this, and we have to consider that dp1 is going to be 0, right? dp2, yeah, what if the number here is 3, right? Number here is 3, and we're going to shave 1 off, and then that's going to be 0, doesn't really matter. So now we're going to say 2 minus 1, that's 1, right? And we don't do it, so now we need to calculate dp1. Hold on, dp1, so what is that? That's the number of digits. If the length is 2, if the length, right, that's length is 2, right? And we get the remains. And should we look at length 2? Right? If this length we already have, then we just return. If it is not, then we need to compute the length minus 1. All right? And length minus 1 is going to be 1. Now, the edge case, let's say dp2 is going to be 1. 2 digits is going to be 1, right? So in here, if we're passing 3, that should give us 1, right? We're passing 3, it should give us 1. And we'll say bin length is 2, and the remains will be bin length is 2. Ah, it didn't even fit here. It didn't even fit. Oof. We have to set this is the beginning, right? So like if its number is 3, I don't even have bin length cannot even minus 3, right? So why actually left shift 1? Bin length is 2. Hold on, this doesn't make any sense. Oh, no, bin length is, oh, I'll have 2 more, so there's 4. Shift 1, that's fine. So it's going to give us 1. The remains equal to 0, so it doesn't matter. So we're going to look at dp2. If we have it, then we return, right? If we don't have it, actually edge case in front. Say if n is smaller or equal to 2, that is going to return 0. No, not return 0, return 2. Return n, right? But actually not return n. How many number integers? So if it's 2, n equals 2, output should be 3. Yeah, so n plus 1. N equals 1 is going to be 2, right? That's the edge case. And then here, so pass in, the minimum is 3, right? 3 pass in. We should check 3, right? And if 3 is not, so bin length is not, now 3 it is. Now if we, now bin length is 2, right? 2. So we check if dp bin length, right? That's actually not right. It should be, because this is the number. It has to be bin length minus 1, right? If bin length minus 1, how do we do it? So if it's 3 and 3 bin length is 2, and we check dp1 doesn't have anything, so we have to calculate dp1. There's nothing to calculate. Nothing to calculate. So I think this is also an edge case, right? So if n is smaller or equal to 2, if n equals 3, that's going to be 2. That's going to be 3. Okay, that's the other edge case. Because then everything else, then we can calculate. Yeah, because we don't have dp1, but we do have dp2. So if I give a 3-digit number, right, coming in, then we can compute whatever this one is, right? And then we can compute dp2, right? So like how many these things are. Okay, so for this, if n equals 3, that's going to return 2. Now these two, I think these are the edge case. Now coming in, there will be at least 3 digits, right? At least will be 3 digits. Now if it's 3 digits, if it's 3 digits, actually, helper, we can actually increasing this. We say if n is smaller or equal to 2, right? If it's smaller or equal to 2, that's going to return 0, right? If n num is equal to 3, that's going to return 1, right? If that's the case, then we don't need this. But we still need and this we cannot have. dp2. Binary length. How do we combine these together? Binary length minus 1, right? And that should be fine. How do we compute? Then let me say we don't compute that. Okay, here's what I think. No, I don't want to do this. And this has to be if len dp is larger than 2, then we do this. Otherwise, we don't. And then we call helper. Whatever helper is, eventually we're going to call helper n, and we're going to return this. Right, this is the structure. So we have, these are the edge cases. Now we get the binary length of the current number, and we get the remains, which we're going to call helper again, right? The remains we're going to call helper again, and for the ones we have, we're going to go binary length minus 1. Now we say binary length minus 1 if we have the value for it already. That's good, right? Oh, hold on. If you say it this way, I shall be fine because we compute this, right? So we compute the remains. The computer remains. And then we have this. How do we populate a DP table? We say if it's good, then we return. If it's not good, then we have to go. From somewhere, right? Because we kind of from top down, not bottom up. Remember that this is like kind of backwards. What we're doing a little bit backwards. So we say if this one doesn't have it, then we need to check if bin len -2, if we have that. Actually, not bin len -2. It's going to be bin len minus, I think it's -3, right? So we look at bin len -1, like just everything that's up into that, and then we're going to do in the DP bin len -1, that's bin len -1, -2, -3. Yeah, we're going to do -3, bin length -3. We're going to do all of that, and then we're going to check this. What if we don't have this? Ooh, this is. I think we need two things. We might need two. Or, you know what? We pre-populate it. Like, screw it. We just pre-populate the DP table. We don't care because we know the largest value is 10 to the 9th, so we can compute every single thing inside here. But if you look at it, it's not that much. It's not that much. So here's what I think. I think we need to call DP equal to, this is like shared by all, yeah, let's do this. Screw it. We're gonna have, this is gonna be 10 to the 9th, right? And then we're gonna compute it, right? So we know dp2 is going to be 1, right? And we say for, let's go, max len equals this. Yeah, it's going to be the max len, right? And then it's going to times max length. And remember, right, it's actually half to max len plus 1. And then dp2 is two digits is 1. And for I in range from 3 digits all the way to max len plus 1, is max len digits, what do we do? What we do is, now we have 3 digits, so we say we secure the first one, secure the second one, right? So I is the total number of digits, right? So I minus 2, so I minus 2 is remaining, and then we say 2 to the power of this, which is similar to say 1 left shift this, right? So 1 left shift, here is 1 time, so that's 2, right? So it's going to be this dpi equal to this. That's the first. And then we're going to say for j, right, j in range, that is going to be I all the way to where? All the way to where? All the way to 2, right? All the way to 2. Because 2 digits, that's the minimum. And then 3 digits, 4 digits, so maybe 2 to I minus, I think it's I minus 3. Because that's I, right? Minus 1, minus 2. Oh, actually, no. Actually, it's also minus 2. I and minus 2. So pick 2, right? That's the, and actually it has to be plus 1. So in this case, 3 minus 2 is 1. 1 plus 1 is 2. So this one doesn't do anything. What I'm going to do is dpi plus equal to dpj. Because we built up, so we can do this. And after we finish, dp is done. Right? Now, when we do this, we don't need to call helper. I think we can just go right into it. We can say if num is smaller equal, if n is smaller equal to 2, done this. If n equals 3, that's actually I think we can do this, right? And we can say if not really, not really. So if it's 3 equals 1, right? So we get these are the edge cases. Now with the remaining, and this we're just gonna call self dot find integers, right? String length, whatever. So binary length, that's just -2. So these will be easier to understand. So just -1, right? So bin length -1, one left shift that many times. So this is the remaining value we're gonna do. And now the bin length, if bin length -1, yeah, that's the, like we have 5 bin length and we have 4. So we need all of them, right? So we simply repeat this, that's perfect. Otherwise, oh, there's no otherwise. That's it. Because this definitely works, because I already set up. So this will work. So that's the answer. And we can actually put this one here. It's a tail recursion, actually. Yeah, this is a tail recursion, which means it's possible to write that into a loop. Yeah, I think we can write this into a loop. Let's just say, no, this is easier for me to understand. All right, so let's just test this. Now we can have lots of tests. We can do like the stupid way. So again, 5 can return. Oh, that's not true. This function is looking for all the values, the number that is consecutive. Mister, that is not the one. That's not the one. That's not the one. We have to go def helper. Yeah, man, yeah, that's not the one. Let's just say count consecutive. Count consec. All right, that's the number of consecutive divs up into value n. Right, if num is this, return 0. If num is this, right, and bin will be this. It's not enumerate, it's just num. That's going to be num, right? And dp this plus no. It's going to count. It's consecutive, right? It's a count consecutive. This function. What it does is to count the number of consecutive, and what we have is going to return n minus count consec n, right? No, n plus 1. N plus 1 minus count consecutive. Well, if we have input is 1, all right, this one was 0, so 1 plus 1 will be 2, yeah? If it's 3 coming in, 4 minus 1 is going to be 3. That's not correct, because if number is 3, oh, I actually don't have 3. 3 is 3, yeah. So 5 is 5, 1 gives us 2, 2 gives us 3, 3 gives us 3, which I kept writing 4, give us 4, right? And 5 gives us 5, 6 gives us 6. We only have 1. 7 actually gives us 6, right? Alright, let's try this. Find integers. This is going to be n. Type error. Max length. Okay, I forgot to do length. And this one doesn't have length anymore. Name dp is not defined. Where? Of course dp is not defined because it has to be self.dp. They're all pass. Let's do a big one, which is going to be here. Of course, the biggest one is just 10 to the 9th, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll run it. See well, how we get. That is not correct. My answer is way bigger. So let's see, where do we diverge? Oh, 100 already diverge. 10. I don't have 10. Oh, 10 diverge. Let's just do 8. Put in here. 8 shall be 6. Expected is 6. 7 is 6, right? Yeah, 7 is 6. 8 is 6. Oh no! 7 is 5. Oh, I got these wrong. 7 is 5. Hold on, 7 is 5. How about 6? Oh, 6 is 5. Because 6 is 5. Because there are 2. Yeah, 6 is 5. 7 is 5. And 8 is going to be 6. There we go. So, hold on. How about 4? 4 is 4. Like 1, 2, 3, 4. 4 is 4. 5 is 5. 5 is still good. 6 is going to be 110, right? So 6, 110 should not increment. Okay, let's take a look. 6. Of course, first and most important thing, we're going to print self.dp. That's something we need to see if it makes any sense. 0, 1, 2, 3, 4, 5, 6. That looks fine to me, right? That looks fine to me. What does this mean? This is just the total number, right? The total number that's at this number of digits, right? The total number at this number of digits. Total at this number of digits. I think this is correct. The problem must be here. All right, so 6 comes in, right? 6 comes in, and binary will be 3 digits, 110, right? So 6 comes in, going to be 110, and we do this magic, right? So what we want is all the 2 digits ones. So that's going to be 3 minus 1 is 2, so that's going to be 1 plus count consecutive. Right, when I count consecutive 2, because we remove the first one, that's going to be 1, 0. And now we go count consecutive 2. And when we count consecutive 2, we're going to return 0. Because we say up to 2, we have a 0. Right? What we're just saying, 1, 0, 0, 1, 0, 1, 1, 1, 0. Ah, this is the problem. They didn't count 1, 1, 0. How do we handle this? We are handling everything from 1 all the way to 1 something, right? We do handle all of those. And actually, for every number, 1 something something something, we say, what do we say? 1 something something something, right? So we say, what we want to know is how many is from 1 to something something something. But that is ignoring. Yeah, that we ignore something. And we say going to be to 1 1 1 1 1. So all of those, and from 1 to something. From 0 to that amount. That's going to be a problem, because if that amount is leading with a 1, then we're missing things, right? We're missing things. We're missing 1 1 something. So what we want is to count all of this. We can count all of these. Now we can count if it's 1 0 something something something. Then all of this is fine. We can count all of these, right? That's fine. But if it's 1 1, we start from 1 1 0 0 0. That's a different situation. Then we have to count everything, right? We have to count everything as 1 1 0 0 0. Okay. Okay. So that's given. We have all of the but we do dp being length minus 1. That only do that number. What about the smaller? Shouldn't we include that as well? Right? Given the current number, right? We're going to include everything. I feel that should be at the end. That shall be at the end. I don't think that's at this stage. That's not at this stage. Is it at this stage? Come on, think, man, think. I'm worried about double counting. That's what I'm worried about. Right? Because given everyone, we can do a 1 1 something something something. Right? We just see the second. Right? We'll basically just see if the second one is, yeah, we get a binary value, and if the second one is a 1, then whatever the remaining number is, right, then all of these will be counted as have consecutive, right? And this remaining will be given to find. Oh, in that case, isn't that just the total value? Yeah, then that is just the total value of from 111, right? So 10111 all the way down to 0. So we get that, and then we get, hold on. So what you're saying is we want to do accumulate. So the dp equals, let's import iter-tools import accumulate, right? So what you're saying is dp equals to accumulate dp, and let me turn that into a list, right? Because we have to add them together, right? So that's the actual dp. So dp represents the total number of numbers that contains consecutive ones from 0 all the way to 2 to the n minus 1. That's what dp means. And when we go into count consecutive, right? Count consecutive, when we're counting, it's actually we don't need to count consecutive, right? We don't need to count because we're going to get the binary. I say binary str is going to equal to bin n, right? So this is the binary, and we say edge case if n is smaller or equal to 2, that's going to return. No. I still think we need to count consecutive. This will make it easier. And then we're going to just do this, right? And then we get the binary value, right? And the binary value will start with 1 no matter what. So we're going to check the second binary value, right? We don't care about the second binary value. We don't care about the third binary value. And the third binary value, that's the remaining. Because those we're going to handle all of them, right? So it's going to be len bin str minus 1 minus 2. So this is minus 2, right? If we're minus 2, that's the remaining, right? That's the remaining. We need to find how many we have. And in our case, if we give like a 3 digits, right? If it's 3 digits, and then that's going to give us 0 no matter what, right? That's going to give us 0, which is fine. It's going to give us 0. And now what we do is count a 1, 1, right? So if the second is a 1, right, then everything in the remaining will add to it. If the second is 0, then everything in the remaining will not add to it. And that is it. So it's going to be this, going to be self.dp, this line, this minus 2, right, and a plus a value. Right, what's the plus value? Plus value is going to be this thing, right? One left shift, but it's not going to be, this is going to be len binary str minus 2, right? Minus 2, because I want to only go, oh, hold on. No, that's actually a harder way to do. It can be easier. It can be easier. Let's just use, I think, int. We can say base is 2, right? Base is 2, and int binary str 1, 2. So, right? 0, 1, 2 to the end. So it's going to be that if bin str 0, 1 is equal to a 1, else that's going to be a 0. Else it's not a 0. Else it's going to be count consecutive. Oh. So it's the binary string is this, right? Binary remain gonna be binary string 2, and then when I return land binary str. Then we shouldn't do that. We should not do that because the self DP is combining everything. We should only combine it once, so we don't do it here. No. When I return. So what is this? No, we should count everything, but those are different. Right? Those are different. Yeah, those are different. So we count minus 2, so that's the remaining, which is this minus 1 minus 2. So dp on all of this, right? On all of this. That's like a 1, 1, 1. Bless you. It's going to be a 1, 1, 1. Right? Let's say that's a 1, 1, 1. So everything, a 1, 1 all the way down, right? That's what we want. Then plus, right? Plus, it depends if, right? If binary this it was 1, then we're going to say just going to be int binary remain. Int bind remain. Actually, just int here. Right? This int is the last 0, 1, 2. Right? So the last one, last part, and we are going to go. Again. What are we saying? What we're saying is, given that digits, right, that number of digits, how many there are, right? We say we're going to set it to 1, 0 something. Right? Because 1, 0 something, because we're going to say from 1, 0, 0, 0, 0 all the way to 1, 0, 1, 1, 1. All right? 1, 0, 1, 1. And that is actually not true. That's only true if it's 1, 1 something. If it's 1, 0 something, then we need to find all of those, right? We need to find all of those. So it's going to be if bind str 1 is equal to 1. That's the thing. If it's equal to 1, then we need to split into 2 considerations, right? First consideration is, let's suppose it's a 0, then we have the remaining, and we have to go from 1 all the way to 1, 1, 1, and everything. So it's going to be, we're going to have to return, right? Return self dot line binary str minus 2, right? Everything, right? That's a DP, that's everything. And plus, now because it's 1, I'm going to plus the total number, right? The total number, which is binary remain, right? So 0, 1, 2. So there's 1, 1, something, something. So all of these. Else, if it's not equal to 1, right? If it's not equal to 1, which I don't need to write else, which means it's a 0, then what we need is we're going to return, because 1, 0, something, something, something. So 1, 0 doesn't create anything. So we do need to do a count consecutive binary remaining. Because that will be exact same as count remaining. And then we go again. And I'm pretty sure this one is, we can say from tools import ARU cache. I think this one we can cache it. And max what? I think it's max size. Yeah, max size equals none. And then we return this. Nope, still not right. All right, let's don't panic. Let's first of all print self.dp. Let's take gauge. Yep, let's add them together. That's what we want, right? Now, what we're doing is to find the number of consecutive n, number of consecutive n has to be the total value from 0 to n. But I don't think that's the one that you're looking for. You're not doing that, right? I'm not doing that. I'm not doing that. What I'm doing is consecutive this. Shouldn't you be adding if it's equal to 1, then the number of consecutive. So I am only considering, right? I'm only considering this is, no. What this one does is number of consecutive from 0 to the given num, right? Number of consecutive from 0 to num, right? And we split out this problem because I know the number of consecutive from 0 to whatever bind str minus 1. We know all that. So those taken away, don't care. Now what I care about. So what we need to do, this shall be, I think it's going to be self.dp len binary str minus 1 plus. Because minus 1 is the total, like this plus this plus this, like everything from 0 to whatever that number is, the total value, and we're going to plus whatever is inside there. So I think that might be able to do count, right? Binary remains. Try it. This one pass. Okay, that's a good sign. Okay, we pass more and we fail a few. So 0, 1, 2, 3, 4. These all pass. 5, 6 fail. So let's try this. All right, answer is 5. Result is 6. We're passing 6. And still, the problem is with 6. So 6 is 1, 1, 0, right? And again, we're going to print out self.dp. All right. So in my logic, we're going to count consecutive 6. So it's just how many from 0 to 6, right, have consecutive 1s. Now we say no, no, so that's going to be 110, and remaining is going to be 0, 1, 2. Remaining is 0. Remaining is 0, right? And if binary 1, that's 1. So we do this. So we're going to return dp lamp binary. So lamp binary is 3. 3 minus 1 is 2. So we're going to print dp2, 0 and 2. So that's 1 plus self.dp and line minus 2. So 1, that's 0. This one is 0. So like we suppose this is 0, right? And then we're gonna have all the combinations. And now, and plus binary value is 0. Ooh, that is the problem. It should be bind remain plus 1. Right? Whatever value it represents should be 0 to this. Yes, yes, that's going to be plus 1. Then I think we shall be good. How about the others? Others all pass. All right. Now we can try. So let's do this. Come in here. 100 first. Yep. 3, 4, 5, 6, 7, 8, 9. Let's see. Yep. Submit. Pending. Judging. Ah, runtime error. Maximum recursion depth exceeded. That is very interesting to say the least. 20. How? What's 20? $20 is 10100, right? Maximum recursion. How? So 20, let's do it. 20 comes in, right? 20 comes in, and binary we have. Binary remain is going to be 100. No! Binary remain is going to be, it is 100, right? 10 is actually is 5. So binary remain is 100, and is 1. No, it's not 1. So it's going to equal to dp4 plus count consecutive binary remain, which is 5, right? Count 5. Now 5 comes in, and we did 5. 5 is fine. Why does 20 give us trouble? I don't know, just put a number there. Maximum recursion, yeah. I don't understand. Let's print num. Of 4. Oh wait, no, 100 is 4. Why did you say it's 5? But we have 4. Num is 4, right? So binary is 100. Remaining 2. Shouldn't that be 0? Remaining is 0. And Wait, what? Doesn't make any sense. What? Oh, shoot. Typo. Typo. Ah! That should be, yeah, this is a typo. N. That should be 12. Yep. Wow, how is this not discovered earlier? All right, try it again. Submit. Pending. Judging. Got it. Nice. Very nice. Wow, imagine how you're gonna do it. How am I gonna say? Yeah, it takes some efforts. I don't think it's like difficult, but it does take efforts. Okay, so let's explain this thing. So first of all, we create a DP table that gives us the total number of values from 0 to 2 to the k minus 1, right? 2 to the k minus 1. That contains consecutive ones. This can be done like this. Given some value 1, 1, 1, 1 with k ones, right? The number of the number of values with consecutive ones from 1, 0, 0, 0 to 0, right? With k minus 1 zeros to 1, 1, 1, 1 with k ones is the number of values with consecutive, let's just call it, and let's call a value with consecutive ones a target value. I say, given this number of targets from this, right, with k on 1, 2 with k ones, is the number of targets, right? The number of targets from 1, 0, 1, 1, 1 to the 1 plus 1, 0, 0, 1, 1, 1 to the 1. Actually, I'm gonna go this plus 1, 0, 0, not 1, 0, 0, 1, 0, 0, 0, 1 1 plus plus number of in 1, 0, 0, 0, 0 plus 1, 1 everything. This is a nice repeating problem. It's a nice repeating problem, and we can obtain the number of targets in each
touch it.
Alright, I'm back after some detour. Alright, let's continue our explanation. I don't like how I explain it. It seems to be too complicated. Alright, I'll do this again. The total number of values from 0 to... let's create a DP table such that dpk gives us the total number of values with consecutive ones. Let's call it targets from 0 to 2 to the k minus 1. Right? Oh, this feels like BIT. I'm basically implementing binary index tree. We should try that. But anyway, so get a total number of values, but consider one from 0 to 2 to the k minus 1. Right? To compute that, to compute each dpk, we first compute the number of targets, right? Number of targets from 2 to the k, 2 to the k actually minus 1, 2 to the k minus 1, which is from 1, 0, 0, 0 to 0 to 1, 1, 1, 1, 1. And then this is going to have with k zeros, right, to this with k ones. We can divide this problem into sub-problems. We know every value that starts with 1, 1, something, something, is valid. So we at least have 2 to the k minus k minus 1 and k minus 2, right? Or at least have 2 to the k minus 2 targets. Then, given 1, 0, something, 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 right? Given 1, 0, something, 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 then the total number of targets is the same as dp. Oh, I shouldn't say. Let's say dp acc, right? Make it more for dp acc. These are all dp acc. And this is going to be dp cc. Yep. So it gives the total number of values, consecutive ones, from this, right? 2 to the k zeros with at least have targets. And the targets is the same as dp k minus 2. Given 1, 0, 0, dot, 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 the total number of targets is dp. I shouldn't say is the same. Let me just say is dp, right? And this is dp k minus 3, dot, 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 right? etc. DC. Thus, we can compute dpk equals 2 to the k minus 2, right? Plus dp k minus 3, then k minus 2, plus dp k minus 3, plus dot dot dot, plus dp 1. Right. After computing the dp table, we perform prefix sum to obtain a dp ACC for future use. Then, given any n, we can write its binary form as 1, 1, 0, something, 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 right? Or 1, 1, something, something, something. I have two situations. If it's 1, 0, something, 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 then the total number of targets from 0 to n is the same as from 0 to ba 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 da 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 da, right? To actually, let me just write it out. To 1, 0 da 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 is the same as from 0 to this. Oh, hold on. And if it's a total number of targets from actually 1, 0 da 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 to 1, 0 this is the same as from 0 to this, right? So the result, so the number, so the total number of targets with, actually, with, let's say, m number of x's. If it's this, then the total number of targets from this is m plus 1 zeros to this m x's is the same as from 0 to this m axis. The total number of targets from 0 to 1, 0, da da da, da, m axis is dp. We call it m axis, so dp m, plus 1 plus find integers, da da da, da 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 da, right? If it's 1, 1, da da da, da, right? If it's a different one, then we need to split into further considerations. Then then we split the number up into two parts. 1, 1 0, 0, 0, dot, 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 0 to 1, 1, dot, 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 and 1, 0, 0, 0, 0, dot, 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 0 to 1, 0, 1, 1, 1, dot, 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 1. The first split has total number of targets, dot, 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 plus 1. And the second split has total number of targets, dp, m, minus 1. Yeah. No, I shouldn't say m, I should say with m number of digits. Because then the total number of is this, it's actually the m minus 1 zeros, right? And this is m minus 2 axis. Same 0 is m minus 2. M minus 2 axis is dp m minus 1 plus m minus 1 plus this. If it's this, then I'm 2 parts, this and this. Split total numbers. This. Right? And this is going to be m minus 2 axis. The second split has total number dp m minus 2. And that's it, minus 2. So it's m minus 2, right? And then plus this. That's plus 1, yeah. Thus, the total number of targets from going to be dpacc, not just dp, it's dpacc. So numbers from 0 to 1, 0 to n is dpacc is dpacc m minus 1 plus one of the 2 scenarios described above. Note that dp acc n minus 1 is the total number of targets from 0 to, yeah, I think I know what this means, so let's gonna do this. Yep, so I don't know, runtime. I guess it's going to be a login. I think it's login. Because every time, it's login, and we run at 32 milliseconds, or 84% runtime. Alright, so this is very convoluted. Hold on, I need to get my cat out. Alright, the cat is out. So I feel like I might be able to do this with not union find, the BIT. So binary index tree, right? So given a binary index tree, we have what? we have query. Query is simple, right? If you want to query this, it's very straightforward. If you want to query, it's just query the value, right? Just query the value. Now we're gonna say the bit gonna store the total number of consecutive ones, right? And we're just gonna be n plus 1 minus query n, right? That's gonna be the result. So how do we build the bit? So we build a bit, push value into it, right? So push value into it, and then at the beginning, it's going to be 0 to a certain value. So what we're going to say is we're going to add a value, right? And initially, this is all going to be 0. And I say if I want to add a value to this, which is the total number, right? Let's add a total number. How do we do it with bit? Because the update is the difference, right? So I'm just saying if we have 1, we have 2. I mean, if we already have it, that's so how so 3 will be 1, right? So over 4, the difference is going to be we can look at how many is we can look at the previous one and see if the current one will increase. That might be a valid solution, right? So if I'm at 3 and then 4, right? 4 comes in as 1, 0, 0, and we just check if 1, 0, 0 is a value with a double, and it's not. So we're going to repeat whatever the 3 is. So we're going to query. So we're going to query the previous one. Interesting. We're going to query the previous one and then add the current one. Is there a faster way to see if there are consecutive ones? Well, is there a faster way? I mean, there is a faster way. If every value coming in, right, and we want to find if it's has a consecutive, we check the second. The first will always be 1. We check the second. If the second is a 1, that it is. If the second is not 1, then we check the remaining, which if we set up which is like from this to this, right? 5, 4. That's possible. Yeah, I think it's possible to do BIT, but I need to first came out the BIT. So I think what a snippet, useful snippet, BIT. Yep. This is a BIT query and size of the range, including min and max. So this is solution 1, right? And try solution 2, use BIT. So it's BIT and solution 2. The function, say class solution 2, right? So BIT, what is n? size of the range, including min and max. So we say bit equals bit 10 to the 9 plus 1. Right? That's including min and max. Now we're going to build it first, right? Now we just say bit.update position instead of range. So when you say bit.update position 0, that's going to be 1. bit.update 1. No, these are zeros. These are zeros. And bit.update. We can just do for n in range 2. No, it is 3. And bit update I 0, right? And 3 and update 1. Now for I in range 4, 10 to the 9 plus 1. And all this, I'm pretty sure we should be able to do it here. Right? So we can do self bit later on. Right? So in this, when the bit need to update, right? Update. So well, first of all, we check the binary str equals bin I 2, right? And we say if bin str 0, 1 is equal to 1, then bit.update I, right? What do we update? We're going to update bit.query query I minus 1, right? And we want to know I minus 1 plus 1, right? That's just the previous, that's the total number, right? The total number up to, oh no, that's just 1. That's just 1. So that's if the 1 position, we just update bit because I is a 1, right? Else bit dot update. So I don't know if I am or I am not. So what I'm going to do is I'm going to update. That means this is 0. So we need to do the remaining. We need to want to know if the remaining is true or false. So when we say remain equal to int bin str 2 to 0, 1, 2 to the end, right? So we have this, and we're going to say bit dot query remain minus bit dot query remain minus 1. So this one is like the remaining if that is a 1 or it's not. So we need to do this. We're done. Now we have bit, right? After we have bit, this one is going to return n plus 1 minus self.bit.query n. All right, let's try solution 2. Oh, shoot. That is not right. So we're doing this. Hold a sec. No. Come on. Cancel. What if we don't go so big? What if we go 10? Because actually 20, 21. Why? because BIT is huge. So BIT needs to be small, like 21. Because we have to do every single one. And this one might time out because the n could be huge, and we have to go through every single one. Initiating BIT is going to take ON, but this is going to take a long time, like seriously long time, and I don't think I can afford it. BIT will work, but it's not going to work the way that we want. So I'm going to beat BIT n plus 1 is going to be n plus 1. Don't self-out bit. So it's going to be bit. Yeah. Yeah, I don't think it works for large numbers though. Okay, this one is going to time out. Small values, fine. Like even like I think 1,000 will be fine. BIT is not defined. Of course, it's not defined. So I didn't define it. I think small value will be fine. Oh, yeah, small value is fine. This maybe, but that's still already pushing it. This probably just gonna go 500. And if we submit this, I think we're gonna time out. Depending on how lenient it is. No, it's gonna time out. Yeah, the problem is not with BIT. The problem is with, 1, 2, 3, 4, 5, 6, 7. We time out at 7. So it's good that we tried BIT, but BIT ain't gonna work. It has to be this, because this is O log n, right? We never, like this part is O log n. And this part is O log n as well. So BIT is not gonna work. So this is just for fun. I tried BIT, but it TLE because the runtime is ON. Actually, ON log n for building up the BIT. Yeah, so it's not going to work. All right, let's go to the solution. Just to check. I'm pretty proud of this. 600. 600. It takes quite a while, right? It takes quite a while to organize our thoughts. Brute force, simple, traverse through all the numbers. Yeah, but it's huge. Better brute force. OX. Result count returned. Bitmap manipulation. Log 2 max. Oh, that's O log n is actually this. Recursion. Wow, that was simple. Better brute force. All right, probably just take a look at better brute force. On any position or not. Instead of this, consider only the required count numbers. In the order of number of bits in the current number, if we get a number at the step 3-bit number generation, this number already contains Use us to generate a number with more number of bits. Append 1, append 0. Reject a number. Ooh, look at this. Wow. Int sum. Again, check. We generate only the required count of numbers. If we generate numbers in the order of the number of bits, current number, if we get a binary 110 on the way at the step of 3-bit number generation. Now, since this number already contains 2 consecutive ones, it is useless to generate a number with more number of bits with a current bit stream as a suffix. The current approach is based on the below. We can start with least significant bit position by placing a 0 and a 1. These two initial numbers correspond to the 1-bit numbers, which don't contain any consecutive ones. Now, taking 0 as the initial suffix, if we want to generate 2-bit numbers with no 2 consecutive ones, we can append a 1 and a 0 both in front of the initial 0 generated numbers. 2-bit numbers ending with a 0 with no consecutive ones. But when we take 1 as the initial suffix, we can append 0 to it to generate 0, 1. But adding a 1 will satisfy this criteria. That's why generating the current number, we need to keep track of the point that whether a 1 was added as the last prefix or not. If yes, we can append a new 1, and only 0 can be appended. If a 0 was appended as the last prefix, both 0 and 1 can be appended in the new bit pattern without creating a validated number. Thus, we can continue forward with the 3-bit number generation only with 0001 and 10 as the new suffix in the same manner. Taking account of numbers lesser than num with no 2 consecutive ones based on the above discussion, we make use of recursion. Returns the count of binary numbers with I bits with no 2 consecutive ones. Sum refers to the binary number generated till now, prefix obtained as the input. Num refers to the given number. Pref is a Boolean value indicating whether the last added is 1 or 0. If the last prefix added 0, we can add both 1 and 0 as the new prefix. That is true. If we add a 0, and we just say every number we generate is a valid number. If we just add a 0, then we can add a 1 or add a 0. But if we add a 1, then we can only add a 0. That makes sense. And the function called I plus 1. What's I? I is the next value. Sum, num, false. That is, we add a 0. Hold on. Wait, what is I? I is position. Oh, I is position. So we move to the next position, right? And we say we add a 0. So the number doesn't change. Right, what's num? Refers to the given number. So the sum is the current value. Or we add a 1. First part refers to 0 being added. Thus we pass false. Okay, makes sense. You can only add 0, thus only one call be made. Okay? So when find, I is the position, right? And the sum is the current value, and number is the target. Boolean is the previous. If sum is larger, return 0. If 1 go that many numbers is larger than num. That means we cannot add a 1 anymore, right? And we return 1. What is this? This is, so like we're given a current value, right? We can either add a 0, right? Or we can add a 1. But what we're saying is, if we add a 1, and that's already larger than my current value, and then I return 1. Which is just add a 0. I think that's what it's talking about. If previous is a 1, then the next position we are going just to add a 0. Otherwise, we're going to add a 1 or we add a 0. But I don't understand this part. If one left shift I position is larger than num, right? Let's see, if we go all the way to the num, right? We go all the way to the num, and we say it's a 0, so next one could be 0. We add a 0, right? You know, we either add a 0 or we add a 1, right? We add a 1. Now, yeah, so this is saying at this position we add a 1, right? Or at this position we add a 0. Now I come out, if it's a 1, and then it's larger than m, I'm going to return 1. I don't understand this part. Return 1. Why? That means we have gone above, right? We've gone above. So the last one added is a 0. And then we go above. Then this one will return 1. And this one will return 1 as well. Because we add a 0. We add a 0. Yep, so that just means we're here, right? Yeah. And then we're going to go, so we're here. 0, 1. And we say we're going to add a 0, right? We add a 0. And then we call this. And 1 left shift 3 times, it's larger. So this is the end. Yep, that return 1, return 1, return. Nice solution. Very good. Very good. We use the current approach, the bit manipulation. Count of binary number with n bits such that these numbers don't contain consecutive ones. Look at the problem in recursion. Suppose if I gives the count of such binary numbers with I bits. Then determine the value of fn, which is a requirement. We can say these two cases. And right? I think it's close to what I was thinking about. Right? We can see that if we know the value of this and this, to generate the required binary numbers, with n bits, we can append a 0 to all valid numbers contained in this without creating an invalid number. It's true. These numbers give a factor of this to be included, but we can append a 1 to all these numbers, so it could lead to the presence of two consecutive decimals. Well, we can do this, right? So if we do this, we can append a 0, 1. This gives a factor, so if n equals this, that's true. Two things first, I think I know what this line is talking about. Let's see if we can understand. That looks awfully like a Fibonacci number, huh? Into 32. Ah, we can do it into 32. 0 is 1, 1 is 2. So 2 to this, everyone is this. That is the same as this, I think. Remember, that's the total number, the total valid numbers, right? It's going to be this plus this, this plus this. But now the problem is to find out the actual value. So I is 30, sum is 0, previous bit is 0. And while I is equals to 0, what is I? Sum is 0. If number, right, is the current number given in end, 1 left shift I, left shift 30 times, so will give us 1 followed by 31 zeros. I think that is the largest 10 to the 9th can get. And 10 to the 9th, I think, is 31 bits, right? 31 bits. So when num and this thing, if it's not equal to 0, then we have 1, 0, 0, 0, or something. So sum plus equal to fi, which means the total number of valid values. What is fi again? The total number of valid values that number of digits. Yeah, the total number of values with that number of digits. The valid number with n bits. Yeah, so the total number with that number of digits, bits. Right, from I bits. Because it's a 1, 0, 0, 1 followed by 30 zeros. Right? That means we can get a total number of bits, sum plus this, which is good. And the previous bit is 1, sum, get a minus minus, and I'm going to break. Now, at the start, the previous bit is 0. I think that's the total number. I think that's the total number. Yes, the total number is a total number of this, right? Total number of this added 0, a total number of this added this. So that's the total number. I think that is the total number. Yes, if 1 is the total number, so that's the total number. So if the previous bit is a 1, then we're just saying we're done, right? Now say the previous bit, but we start with is not a 1, it's a 0. So when I set previous bit to 1, yeah, the previous bit is 1, and then I minus minus. So wait, go one lower. Now when I go one lower, coming back, now what we're gonna say is we're gonna try the 29 bits, right? The 29 bits, and to see if that's a 0. If that's not a 0, that means we have more to come, right? That means the previous one is no. If 1 is 2, if 1 is 2 is 1 bit. We have 2 values. That's true. Yeah, 1 bit is 2 values. That's the total. Alright, so is the total number in that range. Yeah, so we have 1 with blah blah blah. So we just say total value in this range from 1 to this, from 0 to this, everything, right? Everything. And say we're good. Yeah, I think that means everything. Like everything to n bits. Right, everything to n bits is everything to n minus 1 bit. The total everything plus 0. Everything in this, okay? So we say we're going to end it. 1 left shift I position. Right, 1 left shift I position. And we're going to end. And the result is not 0, so it means 1 is something, right? Therefore, we can get I. That's like from 0 to 1, 0 to basically 1, everything, right? 0 to that number of bits, everything we're done. But now we're going to consider the remaining. Yeah, that's why we're going back up. We'll consider remaining. Yes, the remaining. And then if the remaining is also a 1, then we can do this again. Right? Until, but then the previous bit will set to 1. Right, previous is set to 1, so come back up. It's good, so we set it. But then the previous bit, because the previous bit is 1, right? Then we're going to break out. I don't understand the break though. So we get all these, right? So we have only this to worry about. So we num and the remaining, so I minus 1, so it's this part. You're saying this part, oh, if this part is not, so if this part is not equal to 0, if this part is equal to 0, we're just going to go continue, previous bit is 0, I minus minus. That makes sense. We're trying to get the remainder. We're trying to count the total number of the remainder. Yeah, that's the same idea as mine, but much better implementation. And once if it's a 1 again, right? What if it's a 1 again? The previous is 1. My current is also 1, right? And then how can you break out? You should continue working on this. So it's 1 something, so it's 1, right? Something, so we get fi, so that amount, right? If previous bit is equal to 1, which is, so sum with a minus minus. I don't think you should break. Because we still have things remain that we haven't considered. I don't think so, man. I want to try this, but I don't know. All right, how we can find a number? If we fix a 0, of 6-bit numbers. Of 6. Yet now we'll try to fix 1 and a number this or this. This covers the number, but it covers the number in the range beyond them as well. Can't fix 1 and consider all this is bit. Move forward to proceed with a second digit. 0 at this position, we can substitute 1 here. So the result is, see this. One, 2, 3, 4, 5, 6. Yes, F6. Now the 0, we don't consider. Now is this, so we're going to go 1, 2, 3, 4, F4. Right? So we have to keep going. So yeah, so I think this is wrong. You shouldn't break. You shouldn't break. But this solution is worth trying. So this will be our last attempt. I'll call it a day after we're done with this. So this is our official solution. Official solution with bit manipulation. Oh no, got the wrong thing. It's a similar idea as mine, but with much better implementation. We use a DP array to represent the total number of valid values. Note, valid value is 1 without consecutive ones. It can be proved that given k bits, dpk equals dpk minus 1 plus dpk minus 2. Right? Because given any value, if the last digit could be 0 or 1, right? If the last digit is 0, then the total number valid is the exact same as k minus 1. If the last digit is 1, then we don't know, then we have to move 1 more to say it must be 0, it must be 0, 1, and the total number is k minus 2. Right? So that makes sense. After acquiring dp, we consider the given n from the MSB, from MSB to LSB. If the MSB is 1, then result plus equal to dp if MSB is 1, then result equal to dp, how do I describe it? And then we just repeat. say n has m bits, right? If the mth bit must be 1, then result plus m minus 1, right? If then we remove the MSB and continue. If MSB is 0, we don't add to result and remove the MSB. We continue this. We continue this until exhausting n. Alright, so dp is going to be 0 times 32. dp0 and dp1 is going to be 1. dp2 going to be 2. This dp2 is 2 bits, right? So 2 bits will have 0, 1, 2, 3. That should be 3. dp2 should not be 3. Yeah, 2 bits, total 0, 0, 0, 1, and 1, 0. That should be 3, right? Oh, and dp is 0, and dp1. Yeah, so dp0 is 0 bits. That's just 0 itself. dp1 is 0 and 1 is 2, right? And then for I in range from 2 to 32, dpi equals dp I minus 1 plus dp I minus 2. So we get dp, and we say bin str equals bin num 2, right? Now we're gonna start from the 0 position, right? And we say for b in bin str for I b enumerate, right, bin str, we say if b is equal to 1, right, and I'm going to have a rest equal to 0, right. B, if this is equal to 1, rest plus equal to dp len bin str minus I minus 1, right? Yeah. If not, we'll just keep going. If it is, then yeah, I think that's about it. And we return rest. Alright, so if it's a 1, then we know the remaining from 0 all the way to this, all included. And that one is this, right? If it's a 0, then we cannot do anything. We just skip, go to the next one. If it's a 0, then at this position is nothing, right? And I'll go here, then it's from 0 to this, if it's 1, and 0 to here, all included, right? Oh, but there's a catch of a 1-1 situation. If b is 1, then plus equal to this, and then we say if bin str I minus 1 is also equal to 1. right, and then say if I larger than 0 and the previous one is also 1, right? And then what we're talking about is we're counting the valid numbers, and what we're saying is the current value is 1, no previous value, so just the remaining, right? Everything that's valid shall be good, right? Everything if these are valid. Hold on, how does that work? What I'm saying is all the valid ones, but we cannot do that because I'm at 1. I am 1, right? So the remaining, it might have a 1. So it actually has to be this much. All of this valid. That's fine. And then, because if I am a 1, then it's not going to work. So I think I'm deviating from the solution. What I'm saying is, if my current bit is 1, right? If my current bit is 1, then we shall skip. If my current bit is 1, my current bit is 1. It's not my current bit. It doesn't matter my current bit. What matters is my previous bit. If my previous bit is 0, yeah, if my current bit is 1, and my previous bit is 0, then we can add everything. If my current bit is 1, and the previous bit is also 1, then we don't add anything. If my current bit is 0, then we don't add anything. Is that right? If my current bit is 1, and my previous bit is also 1, then we should ignore, because nothing good can come out of this. My current bit is 1. If anything, the remaining will be bad, right? If my current bit is a 0, if my current bit is 0, then that number of bits doesn't exist. So if this, right, if my current bit is 1, we just say if I is equal to 0, or bin str I minus 1, previous bit is a 0, then we can add everything. Right, when add everything, this will be binary str, the length of binary str minus I. What is I? It's current this, and minus 1 is the remaining. We can do all the remaining because my current is 1. No. My current is 1, and the previous is 0. That doesn't make any sense. Hold on, let me do it again. If my current bit is 1, right? So we say we can have all the remaining, right? Be 1, 0, all the remaining. Yeah, like everything. Bad number of bits, everything. But we cannot have 1, 1 something, right? And and that one we're done. Now we go next one. If that's a 1, go with the previous one. So I think what I would do is, if this is current is 1, and if I equals to 0, which means I'm at the start, and or binary, the previous is 0, right? So the previous is 0. So we can do current is 1, right? So my current is 1, which means I have 1 something 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 something. Right? We can contain the entire thing. I have 1 something something. So which means everything in this will work. But I think it has to be -2 because we have to ignore this thing. This we have to say it's going to be 0, right? Else, if I is not equal to 0, and then the previous is not equal to 0, the previous is 1, which means at this position, the previous is 1. So in this position, whatever we do is not going to work. Because the previous is a 1. Hold on. Didn't make any sense. A previous is a 1, and a current is a 1, right? In that situation, nothing good can come out of it, right? So the remaining thing, no matter how they are, is not going to work. So it's going to just skip. And then if it's a 0, then nothing good can come out of it. If it's 1, so I think it's just like that. Do we dare? Oh, we fail. Fail pretty badly. I don't think it's right. Now the DP is going to be right. I think DP we have followed the exact same thing. Right? Yeah. But this part is not right. This part is not right. But I thought I have it. Right? If it's 1, hold on, let me redo this. If it's a 1, then we add current range considered. So if it's a 1, we're going to add all this. How can we add all this? Oh, this is a no consecutive, but it could be a 1. Yeah. Oh, hold on. I think I got confused. No. I got confused. So if it is 1, so that's the remainder. That's the remaining things. Yeah, that's the remaining. It has nothing to do with the current length. I'll just say if it's a 1, that means from 0 all the way to 1, 1, 1, 1, 1. All of these are good. So that's why we added. And if it's a 0, so when we add this, done, we remove it. We don't consider that anymore. Now we go to 0. Now the 0, that means we don't support. Done. We don't do anything. Now I go to 1 again, right? 1 again, and this is to say that everything from 0 to this. But didn't we consider that already? Oh, I'm confused. We start with a 1. Range covered until now. Factor added 6. Okay, that makes sense. 0 don't consider. Oh, shoot. Range covered is going to be this to this. Ah, that makes sense now. So, and the front is 1 something something something. So everything from the start into this will cover the entire thing. And then when we remove it, it's actually we enter this range. So we start from 1 0 0 something. And then if it's a 0, yeah, so we have to, so this is included, right? This is included. That makes sense now. This is included. So we have the remaining. We're going to take a look at the remaining. And if it's a 0, it doesn't support anything. If it's a 1, it will support. So we're going to do all of this, right? All of this, which is just going to be 1, to 0 to 1, to 1 0 0, 1 1 1 1. All of this. They're all supported. Because this is a 1, so all of this can do. That's good. A 0, so next one is going to be 1 0 1 0 0. Yeah, so yeah, so I'm going to do this, and then nothing. The last one come out as 1. It makes sense. Ah, makes perfect sense now. Yeah, so we have a 1, right? The front is a 1. So we actually consider is a 0 1 something, right? So if it's a 1, that means, and the previous is a 0, or the previous is this. That means the remaining of this. So the value ranges all the way to 1 something. So then all of this, right? All of this, they're all good. And now we'll keep going. We'll have a 1, right? And then that means the remaining will have 1 to blah 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 something, right? And then this is the remaining. All of this will be good because they will have a 0 at the front. So all of these will be good. Okay, so that's good. What if it's a 1 1, right? That's current situation we consider. Now, if it's a 1 1, right? 1 and 1. Again, 1 and 1, and what we're considering is, again, it's 1 something something something, right? So it's going to be 0 and all the remainder. Those are all good, right? Those are all good, and those are all good. So it's going to be 1 0 0 0 0 0 to 1 1. So it's 1 1 something something, right? So it's just 1 0. So all of those, that's good, and I don't think it includes it, right? I don't think it includes it. It's just goes to 0 to this. But this, wait, we're counting, right? We're counting. So if it's a 1, we should only remove once. Because as we go through this is the last one we don't add. Right? We just last one we don't add. Yep, that's good. 1, we're gonna add a 4. Right? 1 when add F3, but there's a 1, 1, so we record, oh, we have a 1, 1. Once we have it, and the remainder we don't consider anymore. Because to consider the remainder, we have to keep track of the beginning. So for the beginning, we have a consecutive 1, 1, right? Because that's how we go. We have 1, we got all the remaining, and then we have a 1, right? We can get all the remaining, but we get all the remaining on the condition, right? On the condition, because all the remaining is consider this is a 0, all the remaining, and right, and the condition is that's still good, right? If it's a 1, 1, and we still can get the remaining, because when we get the remaining, that 1 is a 0, right? So that's fine. What's not fine is if we keep going, right? We keep going, and then we have a 1, 1. Then that's bad. Oh, so binary 1. Now we always add this, right? Rest can always add len binary, so total length minus I is actually minus 1, because 1, 3 minus 1, 2 minus 1, so the remaining is 1, right? So this is the remaining. Don't include this, right? The remaining numbers. That's the remaining numbers. So we can always do that. And after we do that, then we're going to check, right? We're going to check. We're going to say if the previous one, right? If I is larger than 0 and I and bin str I minus 1, the previous one, is equal to 1, then there's no point. I'm going to break. There's no point. And then at the end, I see, rest minus equal 1, because at the end we need to plus 1. Beautiful. Beautiful. So we consider given n from, say n has n bits. If the nth bit is 1, then result plus equal to n minus 1. Then we not remove, then we move to m minus 1 bits. If m minus 1 is a 0, right, we keep, we decrement m and keep going. If m minus 1 is a 1, we're still able to do, we are still able to do result plus equal to dp and minus 2, right? So we're able to do that. But since now we have consecutive ones at m and m minus 1, there is no point moving on. There's no point moving on. One trick is to know that or we can just return res. And we don't need to know that. We just return res. Right, no point in moving on. So have consecutive ones, no point moving, no point continuing. Very good solution. Have to add the given and as well. Good God, this is a good one. Tough. This one's pretty tough. This part is easy. The tough part is to figure out this. Yeah, it's pretty fast. It is, I mean, the total number is about the same. Right, it's about the same, but yeah, so like if current is 1, right, we can incorporate everything that's going towards the current 1. So that's why we can add this. But after we add this, we need to check if there's a consecutive 1, that means any of the remainder is no-go. But if it's not, then we can keep going. Alright, that's it. That's it for today. We did solve it ourselves, but it took a long time, and this is a very good solution. BIT is not going to work. But this official solution is quite good. Alright, that's it. I'll see you guys tomorrow.